There's lots of types of problems that we've done now involving multiple forces and Newton's second law. It started off a while ago now with problems like this. Maybe you got a force acting to the right, you got a force acting to the left, you got another force acting to the left. We needed to find the acceleration of that system by saying F net is equal to F1 plus F2 plus F3, and then we would sub in m times a for F net, and then we'd solve for the acceleration that way, making sure we take into account the directions of the forces and so on. Okay, that's a pretty straightforward multiple force problem. But in the end, it's not much different than the other multiple force problems that we've done that seem a little bit more complicated. Questions like those elevator problems that we looked at yesterday. You get a guy in an elevator, you got a force of gravity acting down on the guy, and you've got, let's say, a normal force acting up on the guy. We're going to treat that exactly the same way. Once we have a free body diagram drawn with more than one force, then we're going to say F net is equal to the sum of the forces. In this case, it's not F1 plus F2 plus F3, rather it's Fn plus Fg. Fn would be a positive value there, and of course, Fg would be a negative value. Just out of curiosity here, though, a couple quick questions on this one. First of all, is this guy in this elevator accelerating upwards or accelerating downwards from this free body diagram? Can you tell me whether it's accelerating upwards or downwards? Fraser's your hand up there. Is he accelerating upwards? Why do you say he's accelerating upwards? Because the force of gravity is bigger? Okay, if the force of gravity is bigger, then which way is he accelerating? Yes, you do. What is it? Yeah. If the downward force is bigger, then he's going to accelerate in the downward direction. If the normal force is bigger, he'd accelerate in the upward direction, right? All right. Another thing is, I could ask you in this question to solve for the normal force, not just the acceleration. If I asked you to solve for the normal force, then, of course, you'd go around, you'd plug your numbers into that equation, you'd do it. But I could also ask you to solve for the apparent weight of the person. I could also ask you to solve for the force of the floor pushing up on the person. In all of those cases, we'd be solving for the same thing. It would be the normal force. Right? How heavy you are is the force of gravity. How heavy you feel is the normal force. So if you ever get a question where you're asked to solve for the apparent weight, and there's a good chance you will on a quiz or a test, then make sure you solve for the normal force. That's a pretty common question. Okay, if you're asked for apparent weight, solve for Fn. Whatever the context, even next unit, we're going to do circular motion. Okay? And we're going to spend some time doing problems involving, you're going on a roller coaster loop. How heavy do you feel at the top of the roller coaster loop? You're still solving for the normal force. Okay, so remember that come quiz time or come test time. I could ask you for the normal force, but I could ask you for the apparent weight or the force of the floor. In any of those cases, we're still looking for the normal force. All right, we finished off yesterday with problems that look something like this. Call them pulley problems. Maybe we've got a couple objects hanging over the edge of a desk with a couple pulleys on the end of it. Maybe you've got an object in the middle. Maybe you don't have an object in the middle. We have to be able to analyze that one as well. Well, this one's a little bit trickier because we've got two forces here, the force of gravity acting on object number 1 and the force of gravity acting on object number 2. And they're both in the same direction, but yet they oppose each other. Okay, they're both pulling on the system downwards, but downward caused by number 1 pulls the system to the left. Downward caused by number 2 pulls the system to the right. We have to have a way of accounting for that. We're not going to make them both negative forces here because we want to make sure that we distinguish between these directions. If one is pulling the system to the left and one is to the right, then we have to make sure that we make them opposite signs. The way that I do this to help me remember that is to straighten it out. That makes Fg1 acting to the left and Fg2 acting to the right. Remember that force of gravity is never acting to the left or right. It's always acting down. But we're pretending it's acting left and right just to remind us that we have to make one of them negative and one of them positive. All right, at this point, we would do the same thing as we do for all the other problems. F net is equal to the sum of the forces, Fg1 plus Fg2. And then we would sub m times a in for the net force. Yep? Are you sure? Okay. Now the only other thing that I could toss in here to make it a little bit more tricky is, what if there's a force of friction? Let's say there's a force of friction acting this way on that middle object. You wouldn't get friction on these two guys because there's no contact with the desk there, right? But if there's a force of friction on the middle guy, then, of course, we just plug in another expression there, FF. Okay? Sorry, say it again. The effect of the force of gravity is applied on the middle object. I'm not sure exactly what you mean by that. There is a force of gravity acting on the middle object directly, right? But there's the normal force. There's the normal force which cancels out there. Sorry, go ahead. Yeah, yeah. I'm still not sure exactly what you mean there, Rucker. You know what? When we get doing a couple problems, and just call me over, and we'll work on it. We'll work on it, just you and I, and we'll see if that works. Okay. All right. We had a couple questions for homework last night, guys, and those questions for homework were on this stuff right here, these Pauli problems. Again, same thing as all the other problems, really. We just straighten it out, make it a little bit more complicated, but not much. Problem 1, page 157, problem 2 on 157. We got both problems going back to figure 3.48 from example 3.11. Any issues with either of those questions, 1 or 2? Yep. Number 2. Anybody for number 1? Are we good for 1, or should we go over number 1? We're good? All right, let's take a look at just number 2 then. It says if the tire in 3.11 is replaced by a car tire of mass 15 kilograms, so that becomes 15 kilograms. That's the acceleration of each object. What was B? What was pale B? If we go back to the example, 20. No. B was 8 and C was 6. All right, there's no friction in here, I don't think. Let's straighten this out. Here's pale B, here's tire A, here's pale C. Pale C is a force of gravity acting on it. We'll just call it FC. Really, it's a force of gravity, but we'll simplify it by calling it FC. It's equal to 6 times 9.81, which gives us 58.86. Is that right? 58.86? I believe it is. The force of gravity on object B, it's a little bit bigger, so let's draw it a little bit longer here. It's going to be equal to 8 times 9.81. Somebody tell me what 8 times 9.81 is. Yep. Hayden? 78.48, thank you. 78.48 newtons. Now, there is a force of gravity acting on object A and a normal force. They cancel, so we're not going to worry too much about them. We want to find the acceleration now. So the net force is equal to the sum of the forces. It's going to be, call it FB plus FC. Net force is m times A. What mass do we use here? Do we use the 8, the 6, the 15, or some sort of combination of those three things? No, not the 15. Remember, if you're analyzing the 15 kilogram object only, then we'd use the mass of the 15 kilogram object. But we're analyzing the entire system here, so we're going to use the mass of the entire system. So that's going to be, what is that, 29 kilograms times the acceleration equals FB. I got negative 78.48 for that, although Travis might have positive 78.48 for that. For FC, I've got 58.86 newtons. Travis might have negative for that. And that's okay as long as you're consistent through your question. If you make this negative, this has got to be positive. If you make this positive, this one's got to be negative, right? Doesn't really matter which way you go as long as you're consistent. All right, so we get 29 kilograms times the acceleration equals neg 19.62 newtons. Now we're going to solve for A here. When we do that, I assume we get 0.68 or negative 0.68 meters per second squared. Now we're asked in question 2 to find the acceleration of each object. I've just found the acceleration of the system. Put it away and leave it away, okay? I've just found the acceleration of the system. That means that the entire thing is going to the left at 0.68 meters per second squared. That means object B is going downwards at 0.68, object C is going upwards at 0.68, and object C, object A I should say, is going to the left at 0.68. That makes sense? Good with that? How many people got that? Okay. Give you a chance to copy that out if you don't have it already. Here's another one for you. Completely different here. Or at least it appears completely different. This one's a block on a hill. We want to find the acceleration of the block. Really, in the end, there are some differences in this question than there have been the other ones. But the basic way that we deal with this is still the same as the way we've dealt with the other questions. But we've got a bit of a problem here, and I'll explain that problem in just a moment here. Okay? Quick question for you first. What's going to happen to this 3.5 kilogram object as we set it on this hill? It's going to fall straight down? It's going to slide which way? Okay, so it's going to slide down the hill, right? I mean, you put something on a hill, it doesn't slide up the hill. It slides down the hill. That is assuming that you're overcoming the max force of static friction, then it's going to slide down the hill. Okay, we're going to assume that that happens here, that we are overcoming the max force of static friction, because it tells us here that there's a force of kinetic friction. It must be moving, since there's kinetic friction, and if it's moving, it's going to be moving down the hill. Well, what's driving it down the hill? What's pulling it down the hill? Not just gravity, because if it was just gravity, which way would it go? Straight down. And it's not going straight down. It's going down the hill. So there's a force that's got to be pulling it this way. If it's moving down the hill, there's the force that's got to be moving it down the hill. What force is that? Okay, Rutger says it's the normal force. He's on the right track, but he's not quite right. He says the normal force always acts perpendicular to the surface. It does. There's the normal force, but that's not acting down the hill. The normal force is kind of acting up and to the left. Travis? I'm sorry? No, inertia is not a force. Okay, good guess, but it's not a force. Rutger, what were you saying there? Okay, good, good. I'm going to redraw this, and I'll explain what Rutger just said here. There are two forces besides friction. Let's ignore friction for a second. We'll deal with that in just a moment here. Okay? Friction is not what pulls it down the hill, and that's what we want to deal with right now, is what pulls it down the hill. Okay? Watch very, very carefully as I do this. There are two forces that act on this 3.5 kilogram object besides friction. There is the force of gravity that acts straight down, always acts straight down. Whether you're on a flat horizontal surface or you're on a banked surface, a hill, like we are in this question. There is also the normal force that acts. Now, the normal force usually cancels out gravity. It's usually equal and opposite to gravity. But in this case, it's not, because gravity acts straight down, and as Rutger said just a minute ago, the normal force acts perpendicular to the surface, 90 degrees to the surface. Now, watch very carefully here. The normal force combined with the force of gravity give me this force. And if I added those two forces up vectorially, because we're dealing with two dimensions here, then we would get that red force. Does that make sense? We don't know what their values are right now, but we know that if we did know what the values are and we broke them into vector components and we added Fn to Fg, we would get this value. The sum of Fn and Fg, the vector sum of them, equals that red force. That red force is a force, you can see in this picture, that is parallel to the surface of the hill. We're going to call that red force Fh for the force of the hill. And we're going to redraw that red force up here. We're still going to label it Fh. I'm not telling you that there's two Fh's here. There's only one. I'm just drawing it in two places. Remember what we said when we first started drawing free body diagrams? It doesn't matter where you draw a force, as long as you draw it the right length, and as long as you draw it in the right direction. Okay, I initially drew Fh down here, and I changed my mind. I don't want it down there anymore. Now I want it up here. Fh is the force that pulls this object down the hill. And it really is, as Rutger said a minute ago, it really is the combined force of gravity and the normal force. And if it was just gravity, it would go straight down. If it was just the normal force, it would go up like this. But the reality is, it goes down and to the left. The left component of the normal force combined with the down component of gravity pulls it left and down, which means it goes down the hill. Does that make sense? Now, right now, we don't know how to find what that value of Fh is, but we at least know what it is. Not its value, but we know what it is. Now, how do we get that value of Fh? You can see that this angle that we have labeled here at the bottom of the hill is 15 degrees. This angle right here will always be the same angle as that angle at the bottom of the hill. Always. Every single time. I can justify it for you, but in the end you're not going to have to repeat that because it's always going to be the same value. Look, if this is 15 and this is 90, then this one is going to be 75. And if that's 75, then that's got to be 15 because they've got to add up to give me 90. If you don't quite get that, it's not the end of the world because this angle right here will always be the same angle as we have at the bottom of the hill. If we know that angle, 15 degrees, and we know the value of Fg, which we don't really know its value right now, but we can find it real easily. It's m times g. It's 3.5 times 9.81. Then we can find Fh. Let's say sine 15 degrees is equal to opposite Fh over hypotenuse. Right? That's a 90-degree angle, right? So opposite over hypotenuse, which is 3.5 times 9.81. Let's get that value. Let's take 3.5 times 9.81 up by multiplying, multiply it by sine 15 degrees and see what we get. 8.8866 newtons. So gravity is pulling down with a force of almost 35 newtons. The normal force is pushing up and to the left with a force of, not sure exactly. Combined, those two forces give me Fh, the force of the hill. And that's really what drives it down the hill. Now, there is a force of friction acting here as well. The force of friction is going to be 3.9 newtons. Which way does it act, left or right? Up the hill or down the hill? You guys know this. Which way does friction act, Ren? How do you know that? Good. The object moves down the hill. That must mean friction is going to act up the hill. It's going to be 3.9 newtons. Now, you don't need to redraw this if you don't want to. Okay, I sometimes do just to simplify it a little bit. I'm going to do that here. But in the end, if you want to just stick with the diagram that we have on the board right now, that's okay. If I redraw it, I'm going to redraw it flat. Fh will be 8.8866 newtons, and Ff will be 3.9 newtons. And then I'm going to say the net force is equal to the sum of those forces, Fh plus Ff. Hey, when I'm doing this step here, why have I not included Fn and Fg? They don't cancel. Remember what we said with all those other problems? Look, you got an object like this. Here's Fn, and here's Fg. They cancel each other out, so we don't include it there. Fn and Fg don't cancel out here. Why don't we include it when we're saying F net is equal to the sum of the forces? That's a great question. Why don't we include it? Yeah? Yes, you're right. Bottom line is because we already have included them. Right? We do include them. They don't cancel. We do include them. But we are including them already. As Aidan said, we use the force of the hill. Okay, the force of the hill is gravity and the normal force already. So we say m times a is equal to fh plus ff. M is 3.5 kilograms times acceleration equals fh, which is, I'm going to say it's negative 8.8866 newtons plus 3.9 newtons. And then we can do this math pretty easily. When we do, we get an acceleration of negative 1.4 meters per second squared. So it accelerates down the hill at 1.4 meters per second squared. I think that if you look at what's in black over here on the left-hand side, I think it's easy, like really easy. What's in black on the left-hand side there, what's kind of squared off. This is the tricky thing right here, is getting FH. Okay, we have to understand the geometry of this. Right? We have to understand that there is gravity acting straight down, that there is a normal force not acting straight up, but acting always at 90 degrees to the surface. And we have to recognize that the sum of those forces, the resultant force, going from start to finish here, is a force that's parallel to the hill. In other words, it is the force of the hill. It is the force that drives it down the hill. Then we can find its value using some trig, and then we just go back to here where it becomes really, really easy. How would we don't have to do it in this question, but how would we, if we were asked to, how would we find the normal force? Yeah. We're going to use a different color for this because it's not, we don't have to do this. Just kind of a little aside here. Okay, go ahead. Yes. Since the normal force is the adjacent side of that triangle, we'd say cos 15 degrees is equal to Fn, the adjacent side over the hypotenuse, 3.5 times 9.81. Okay? We don't need to bother solving for that because we weren't asked to, but that's how we would do it if we needed the normal force. So for instance, if you were given a coefficient of friction instead of a force of friction, we would get the normal force, multiply that coefficient by that normal force, and then do what we did. Right? Is this stuff okay in here? Okay. Let's give those a try, please.